Okay, guys, we are on section 4.2, logarithmic functions. We're going to start off with a definition. The inverse function of the exponential function with base b is called the logarithmic function with base b. We have y equals log base b of x is equivalent to b to the y equals x. The function f of x equals log base b of x is a logarithmic function where base b, a logarithmic function with base b. Okay, so we have y equals log base b of x is the logarithmic form. Okay, and note that y here winds up being the exponent in a minute, and then we have our b, of course, which is the base, and then we have b to the y equals x, and of course we see here's my base b, and then of course y is my exponent. Okay, this is the exponential form. Okay, so the inverse function, the exponential function with base b, is called the logarithmic function with base b. It's known as y equals log base b of x, and it is equivalent to b of the y equals x. The function f of x equals log base b of x is the logarithmic function with base b. And so we have the logarithmic form, which is y equals log base b of x, and then we have the exponential form of b to the y equals x. So let's look at example 1. Write each equation in its equivalent form, equivalent exponential form. Okay, so A says 3 equals log base 7 of x. B, we have 2 equals log base b of 25. And C, we have log base 4 of 26 equals y. Okay, so guys, this is easier, in my opinion, if you rewrite it as log base 7 of x equals 3, then what we're going to do is we're going to take this 7, we're going to raise it to the third power, and it will equal x. So this becomes 7 to the third power equals x in the equivalent exponential form. Okay, rewrite b. This is really log base b of 25 equals 2. So that's b to the second power is going to equal 25. So that's going to give me b to the second equals 25. Okay. Then on C, if I rewrite that, that's really saying y equals log base 4 of 26, which I don't really need to, I really don't need to rewrite that one. That one was okay. I'm sorry, guys, you probably heard the little dog barking in the back. This is going to be 4 to the y equals 26. So that's going to give me 4 to the y equals 26. That's a strange looking 4 to the y there. 4 to the y equals 26. Okay? All right, let's look at example 2. Example 2 says we want to write each equation in its equivalent logarithmic form. Okay, so we're going to go the other way this time. So on A, I have 2 to the 5th equals x. B, I have b cubed equals 27. And C, I have e to the y equals 33. I'm going to write our two forms over here. Of course, my exponential form is b to the y equals x. We're getting that from up here. Okay, and then my logarithmic form is y equals log base b of x. Okay, so we're going to go from exponential form to logarithmic form. Pay attention to where the base is and where the exponent is. Okay, so I know b here is 2, so that's my base. And I know that 5 is my y, my exponent. So this is going to be 5 equals log base 2 of x. Okay, in B, all right, what is my base? My base is B, so log base B. What's my exponent? That's 3. Okay, and then we have 3 equals log base B of 27. Then in C, okay, who's my base? My base is going to be E here. My exponent is Y. So I've got y equals log base e of 33. You just have to be very aware of where your base is and where your exponent is. Okay, let's look at example 3. Example 3 simply says evaluate. Okay, A, I have log base 10 equals 100. B, I have log base 5, not equals 100, I'm sorry. Log base 10 of 100. It's a little late. Should have recorded earlier, guys, I'm sorry. B is log base 5 of 125. And C, we have log base 36 of 6. And then D, I have log base 3 of the 7th root of 3. Okay, so these are easiest, guys, if you take them and you set them equal to your pretty much what you're looking for. So then that way you can go back and reset them as far as rewriting it as an exponential function instead of a logarithmic function. So you're trying to find the answer of what log base 10 of 100 is. And you can put it in the calculator and you'll get an answer, but they're telling you not to put it in the calculator. They want you to find the answer. So it's easier if you take that log base 10 of 100, that's an actual value, and say, okay, I want to know what that equals. That equals x. And then rewrite it as your exponential function. So 10 to the x should equal 100. So I have 10 to the x equals 100. Well, 10 to what power equals 100? Well, that means x is going to equal 2. So the answer is 2. You won't actually put in x equals 2 in your homework. You'll just write 2 in, type 2 in. Okay, on B, we have log base 5 of 1 over 125, where we want to know what that actually equals. Okay, so what I really have here is 5 to the x equals 1 over 125. Now here's the deal. I know that 125, the first thing I do is I go, well, 5 to what power is 125? Well, I know that 5 to the 3rd power equals 125. Well, how do I get that in the denominator? The way I do that is I'm going to take that exponent to the negative power. I know if I have a negative power on the exponent, that's going to move that down to the denominator, which will give me, if I say 5, guys, to the negative 1, that's 1 over 5. So 5 to the negative 3 would be 1 over 5 to the 3rd power. Okay, well, so, and I know that 5 to the 3rd power is 1 over 125. So I know that x is going to equal negative 3. Okay, C, I have log base 36 of 6. We're asking ourselves, what's that going to equal? Equals x. So 36 to what power equals 6? Well, I know that 6 squared equals 36. So what I'm really looking for down here is I know that square root of 36 equals 6. Well, we have to go back and think, when I write the square root, what's that as a rational exponent? Well, this is really 36 to the 1/2 power equals 6. So I know that x will equal 1/2. Okay, log base 3 of the 7th root of 3 is supposed to equal x. So I've got 3 to the x equals the 7th root of 3. Well, guys, what's the 7th root of 3? Really, 1/7. So 3 to the x is supposed to equal 3 to the 1/7. That means x equals 1/7. Okay. Let's talk about some basic logarithmic properties involving 1. Okay. I know that log base b of b is going to equal 1 because let's think about it. B to the first power equals b. Okay, and then I also have log base b of 1 equals 0 because b to the 0 power equals 1. These are important to know. Okay, we'll look at a few other ones that are important to know in a few minutes. So let's look at example 4. We want to evaluate A. I have log 9, base 9 of 9. Well, okay, we'll go ahead and write B also. And then I have log base 8 of 1. Okay, let's do like we did in example 3. This is really going, okay, log base 9 of 9 equals x. So I've got 9 to the x equals 9. So what must x equal? 1. Okay. In B, this is the same as log base 8 of 1 is equaling x. 8 to the x has to equal 1. What is x going to be? So that 8 to the x equals 1. Well, that's 0. 8 to the 0 power is 1. Okay. Let's talk about some inverse properties of logarithms. Log base b of b to the x is going to equal x, and b to the log base b of x equals x. Okay, guys, these do become important later on. That second one is pretty much like when we raise a square root to a square to a second power, or we take the square root of a square. So I've got b to log base b. That's going to make that chunk fall out. Okay, is what's happening there. So I'm going to squeeze in example 5 right here. And it, of course, says evaluate A. I have log base 7 of 7 to the 8th power. Okay. And B, I have 3 log base 3 of 17. Okay. In A, that log base 7 of 7 to the 8th causes that 8 to drop down. And then in B, that 3 and then that log base 3 of 17, that 3 and log base 3 causes that 17 to drop down. Okay, let's talk about graphs of logarithmic functions. Since logarithmic functions are inverses of exponential functions, we can reverse the coordinates of the exponential function. Okay, it also means that it is a reflection about the line y equals x. Okay, so let's look at example 6. Graph f of x equals 3 to the x and g of x equals log base 3 of x in the same rectangular coordinate system. Okay, so I'm going to start off with f of x because I know how to build the table and get some points with 3 to the x with exponential functions because we've done that. Okay, I'm going to pick a few values, -2, -1, 0, 1, 2. Okay, so when x is -2, f of x will be 1 over 9 because I've got 3 to the -2. -1 gives me 3 to the -1, which is 1 over 3 to the first power, which is 1/3. 3 to the 0 is 1. 3 to the first power is 3. And 3 squared is 9. Okay? Now, that means since they're inverses, that when I go to list points for g of x, all I have to do is flip those x and y's from f of x. So my x becomes 1/9, my g of x is -2, my x is 1/3, I get -1 for g of x, I get 1 for x, 0 for g of x, 3 for x, 1 for g of x, and 9 for x gives me 2 for g of x. Okay, so if I get ready to graph that, okay, so let's graph f of x first, that 3 to the x. -2 is going to give me 1/9. -1 is going to give me 1/3. 0, of course, is 1. 1 gives me 3, and then 2 will give me 9. Okay. Okay, so our usual exponential function there. Now when I get ready to graph g of x, which is going to be the inverse of f of x, I know that when x is 1/9, I get -2. So it's real close here to the y-axis, or the vertical line x equals 0. And then 1/3 is going to give me -1. And then 1 gives me 0. 3 is going to give me 1. And then 9 will give me 2. And 9 will give me 2. 3, 4, 5, 6, 7, 8, 9. Okay. And that will give me a graph close to this. Okay. Now, so this is f of x. This is g of x. And we did have the property there that this would be a reflection over the line y equals x, which we can see right here if we graph y equals x, that it is a reflection over y equals x, if I can graph that properly. Not getting a real straight line, but there we go. Okay, let's list some characteristics of log base b of x. And I will go ahead and I'm going to say g of x since we called it g of x here. You can call it f of x. It's fine. 1, let's talk about that domain of logarithmic functions. In general, the domain of this logarithmic function. And so we're looking at g of x here. So this is who we're looking at. That is going to be 0 to a positive infinity. That range will be negative infinity to infinity, because it does keep going down forever, and although it's flattening, it will continue as x grows larger and larger. The y does continue to increase. Okay, we have an x-intercept of 1. Okay, and we have a y-intercept that does not exist, so it does not exist or none. Okay. Also, I would like to point out here, we're going to have a vertical asymptote at x equals 0, or at that y-axis. And if you'll remember, we had a horizontal asymptote for the exponential functions, b to the x. Okay. While we're pointing out those characteristics of log base b of x, let's also review kind of some rules of transformations on graphs, okay? Because that will help us graph. Review of transformations. And this is kind of just in general. But in general, if I have something where, and we're going to call it A, is subtracted from x itself and not subtracted from the outside of it, but inside with that parentheses, okay? We're going to go a units right. When it's inside with the x, we do the opposite. If we have x plus a, those will be a units left. Okay. Now, let's say it's not inside of the parentheses. Let's say there's x and then we say plus something, or we say minus something. It's not inside the parentheses. So x plus a, then we're going to go a units up. And then x minus a will go a units down. Okay, now remember, this is when we're looking at things like if we say x squared plus a, that's a units up. This is x squared minus a, that's a units down. Here we might have something, if it looked like x minus a squared, that would be a units to the right. Here, if we had x plus a squared, that's a units to the left, okay? Now, also, what you need to kind of keep in mind is if I make that x negative in there, this is a flip over the y-axis, okay? So let's look at example 7. We have find the domain of f of x equals log base 4 of x minus 5. Okay, so I don't really need to graph this in order to see this. I can use those characteristics that I listed down here about the domain, and then I can also use the review of my transformations to answer this. So I know that we usually have a vertical asymptote at x equals 0. Okay, if we have something like f of x equals log base 4 of just x, we have a vertical asymptote at x equals 0. And I can put that here if it looks like this. F of x equals log base 4 of x. Okay, that's going to be a vertical asymptote at 0. We saw this over here. It was log base 3 of x, but it's going to do the same thing, guys. Okay. Now, I also know that since the graph will shift 5 units right, the vertical asymptote will now exist at, let me get the t on there, x equals 5. Okay, so since we're going to shift this whole graph right here over 5 units, that vertical asymptote also moves. So the vertical asymptote will now be at x equals 5. That's also going to change our domain then. So our domain now will be from 5 to a positive infinity instead of 0 to a positive infinity. Okay? Okay, so we were able to do that without having to actually graph anything. We could just kind of talk through that. The logarithmic function with base 10 is called the common logarithmic function. Okay. So it looks like f of x equals log base 10 of x, but it's used so often that we don't actually write the base 10 there. And it is expressed as f of x equals log of x. But that 10, if you don't have a base written down there, it's assumed to be 10. Okay? Let's look at some properties of the common logarithm. Okay? Properties of the common logarithmic function. Okay? The general properties that we have, and this is for any base, so we write base b, are number 1, that's log base b of 1 equals 0. We know that, we wrote that, and that can translate over here to my common log as log of 1 equals 0. Okay? Our general property of log base b of b equals 1 looks like log of 10 equals 1 as the common log. 3, log base b of b to the x, well, we know that equals x, so that means over here that log of 10 to the x is going to equal x. And 4, I've got b. Let me move that down a little bit. I need a little more room. 4, if I have b to the log base b of x, we know that's going to equal x, and it's going to work the same way over here for our common log, that 10 to the log of x is going to equal x. Okay? Along with that common log, we also have what we call natural logs. Okay? So, natural logarithms so my natural logarithmic function is f of x equals log base e of x, but we don't write that. It is expressed as f of x equals ln x. Okay? And that's natural log of x, but we write that as ln x. Example 8 says we want to find the domain of each function. Okay, And A is f of x equals natural log of 4 minus x. Okay. And B is h of x equals natural log of x squared. Now, both of these are going to involve a little bit more work. What you need to see on A and f of x is this is really the natural log of, we start out as negative x plus 4. Well, that looks a little better. But then we have the natural log of negative 1 times x minus 4. Okay, so what happens is we have that x minus 4 right there. We look at that part first. And this x minus 4 tells me that I'm going to go right 4. So if I go right 4, okay, that's going to push that vertical asymptote of x equals 0 to a positive 4, which pushes my domain to 4 to a positive infinity. But we're not done because we have that negative 1 there. And we stated up here in our little review that if I'm placing that negative on the x, it flips it over the y-axis. Well, that's if that pretty much y-axis is my vertical asymptote. Well, x equals 0 or the y-axis is no longer my vertical asymptote. That's at x equals 4. So what it's going to do is it's going to flip that entire function over x equals 4. So it's going to stamp it. Remember how we talked about you stamp on the other side when we're dealing with a symmetry. So now it's going to flip to the other side. So then flip, and that will, instead of going from 4 to a positive infinity, now it'll come from negative infinity to positive 4. Okay. Now let's think about h of x equals the natural log of x squared. Well, guys, usually we can only use positive x's, right? Think about what our domain was over here. Our domain is always 0 to a positive infinity. Now, it's never actually 0 because we've got that vertical asymptote there, but we can only use positive x's. Okay, well, that's because we can't take a number to a power and get a negative answer back. Okay, but if we're squaring the x's, what happens? We take a negative x, what happens to it? When we square it, we make it positive. So that means we can use all the negative x's now because we're forcing them to be positive. So our domain will be negative infinity to 0. Still can't use that 0, united with 0 to a positive infinity. And that sums up 4.2.